Good morning. This is your stat sensei, Mr. Spensei, and this is a warm-up introduction to errors, type 1 and type 2. So, scenario 1, a company that manufactures smartphones developed a new battery that they claim has a 30-month life expectancy. Well, that's important. That's the claim. So that's probably my null, which means that would be my that'd be my population mean. That's my claim. So 30 hours. The distribution of the lifespan of the new battery is skewed with a standard deviation of 8 months. Well, that skewed is a problem. We have a standard deviation that's known to be 8 months. And because it's the population, we're going to be working with a Z, and that's what's indicated here. A consumer group tested a random sample of 60. Oh, okay. So our sample size is large enough that we're going to be normal by central limit theorem. So the fact that it's skewed doesn't matter. And when they tested from a batch of 1,000 and obtained an average life expectancy of 28 months. So they got a sample mean of 28. All right. And they want to test to see if the battery is lasting less than 30. So we have a less than. So this is what we're going to circle. And we have an alpha level of 0.05. That's our comparison. So if we're working with a Z, it's going to be Z equals X bar minus mu, standard deviation of the population divided by the square root of n. Don't have enough room there. But that's what we're going to be looking for. So probability that Z is less than X bar is 28. So 28 minus population mean of 30 over population standard deviation of 8 divided by our sample size of 60. So that's what we're going to be looking for and see what happens. So we're going to go to stat edit on the calculator. Stat edit. Oop, excuse me. I said that wrong. Stat, arrow over to the word test. And we want Z test because we have the standard deviation of the population, which means we're going to work with the Z. Statistics, and we're going to input our population mean. Well, our population mean was 30. So we'll input the 30. Then we have a standard deviation of the population of 8. We have a sample mean of 28. And we have a 60 as our sample size. And we said we wanted less than because they're testing to see if it lasts less than 30 months. When we calculate, we get a z-score of negative 1.936. So the probability that z is less than negative 1.9364 equals this p-value of 0.0264. And I'll need to compare that to my alpha. 0.0264. We'll make these the same length. And 264 is definitely less than 500. So my decision will be to reject the null. So if you reject, you cannot commit a type 2 error. So that eliminates that. All right. No errors could have been committed because the test was run properly. Doesn't matter if you run a test properly. Due to sampling variation, errors could have been committed due to sampling variation. So it'll never be that answer. So we're looking at type 1 or one of the type 1s. Type 1 error was committed. We don't know if it was committed. We know that it might have been committed. Matter of fact, we said, you know what? We don't mind being wrong 5% of the time. And the chance that we'd make the wrong decision based on this sample is 2.64. So a type 1 error may have been committed. Based on our decision making, we were happy with it being 5%, but what we got from our sample is it's no more than 2.6, but it might have been committed. There's a 2.64% chance it could have been committed, but we never know if it was. So we never can be definitive about it. So scenario 2, the anterior cruciate ligament is one of the ligaments that help stabilize the knee. Recovery time from the surgery to repair the ACL averages 224 days. Okay. A medical center believes that they've developed a new procedure which reduces the average recovery. That's probably an important word, reduce. A random sample of 31 patients. Oh, we have a sample size of 31 out of more than 500. That's our population, our group. The average recovery time for those receiving the new procedure was 203 days. And we have a sample standard deviation of 85 days. Well, that's important. The fact that it's a sample standard deviation tells me I'm working with a t. And remember, a t distribution has x bar minus mu sample standard deviation divided by the square root of n. That's the t. So we're going to plug in, and we'll have the probability that t is less than 203 minus 224 over 85 divided by the square root of 31. All right, so let's go test, t-test. Well, our sample, our population mean was 224 days. We had a sample mean of 203 days. We have a sample standard deviation of 85 and a sample of 31. And it said reduces recovery time. Okay, so this is going to be reduced, so we need a less than. And we're testing at an alpha. We're testing at an alpha of 0.05. All right, so this said reduce. That's why we have the less than. So that means I need to have a less than circled. I calculate, and I end up finding negative 1.375. So the probability that t is less than negative 1.3755 yields a p-value of 0.0895. All right. So 895 is greater than 500. With that being the case, we're going to fail to reject. And if you fail to reject, you cannot be type 1. No errors could have been committed. Errors could always have been committed due to the variation in our random sample. So due to random sampling, we could always have an error. Whether we commit one or not, we don't know. And that's the key. This says was committed. It's not was. It may have been committed. And in this case, we said, hey, you know what? We don't mind being wrong 5% of the time. Well, the chance that we'd get a sample like this is 8.95% of the time. So there's 8.95% chance that we'd get a statistic like this. So we're going to fail to reject. All right. So anyway, we cannot say that we did commit it. We said that we might have committed it. We won't know because if we didn't know, we'd go back and fix it. I appreciate you watching. Hope to see you on the next one. Thank you.